Okay, lesson number 2 in probability. My printer was running out of ink, so we get a little bit of a sketchy first page, but it gets better after this. So you guys can also see it on your own notes. So today we're going to talk about mutually exclusive events. So what that means. So when discussing probability, a set of outcomes is referred to as an event. Okay, so like we could have an event where you roll an even number on a dice or something like that. Die, plural. If two events are mutually exclusive, what that means is that they cannot occur at the same time. Okay, another term for a mutually exclusive set is disjoint. Okay, so if we think about that as a Venn diagram, okay, here's event A, here's event B, they cannot overlap. Okay, so we learned about disjoint already, and this is also referred to a mutually exclusive event. Okay, so example, when a coin is flipped, either heads or tails can come up. Okay, so heads or tails cannot both be outcomes simultaneously, right? It's either one or the other, so heads or tails. If two events are non-mutually exclusive, so the opposite of mutually exclusive, that means they can occur at the same time. This is shown by two overlapping events in a Venn diagram. So something like, here's event A, here's event B, and they do have an overlap. So event A is rolling an odd number, okay, so that would be 1, 3, or 5, right? That's the set of outcomes. And event B is rolling a number less than 4, so that would be 1, 2, or 3. So notice how, in this case, these guys overlap 1 and 3. So let's say this one's A, this one's B. A would be 1, 3, and 5. B would be 1, 2, and 3. And then 4 and 6 would be outside, just in the universe. Okay, so we're going to do a couple more examples. So we're determining if each event is mutually exclusive or non-mutually exclusive. So drawing a king or an ace from a deck of cards. Okay, so if you draw one card from a deck of cards, there's event K, we'll call K king, event A for ace. Those two can't overlap, okay? So these are mutually exclusive. Sometimes we just abbreviate that as ME, okay? If we get a number that is a multiple of 3, so remember that would be 3, 6, 9, blah, 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 and divisible by 2 when a dice is thrown. Okay, so if we're talking about dice, we don't need the 9. If it's divisible by 2, that would be 2, a 4, or 6, okay? So these guys, see how we have a 6 overlap? Okay, so this would be non-mutually exclusive. And if it helps, you can always draw yourself a Venn diagram, right? The 6 is the overlap. So let's do multiple and divisible as our set names. So multiples of 3 are 3 and 6. Divisible by 2 are 2, 4, and 6. And then we could write the other 1 and 5 out in the universe. Okay, so that can help you. The Venn diagrams can help, okay? Okay, the next example, drawing a red card or a jack from a standard deck of cards. Okay, so there are jacks that are red, right? So there is going to be an overlap, right? If we call this jack and red cards, there are two jacks, the diamonds and the hearts, that are an overlap of both a red card and a jack, right? So this one would be non-mutually exclusive. They can have them together. Being on the volleyball team and being on the basketball team. There are people who do both, right? So we could have volleyball, basketball. There might be people who overlap. So this is non-mutually exclusive again. And then drawing a red ball or a white ball from an urn of red and white balls. So you cannot do both at the same time. Okay, so this one, we'd have a separate set for each. So this would be mutually exclusive. Okay, so the Venn diagrams can help thinking through that logically. Okay, so a complementary event, so we've talked about this a little bit before, but just as a refresher, so if you use a complement or a apostrophe, that means a complement. Sometimes in the SNAP book it also is a with a line over top, but this I think is the more common. It's also way easier to type, so we use that. So the complementary event is the set of all the outcomes in a sample space that are not elements of A. Okay, so for two events to be complementary, they must be mutually exclusive, right? There can't be overlap between those two, right? Because that would mean if something's not part of a specific set, that means it's outside, right? There's no overlap there. And the sum of their probabilities must be 1. Okay, so we'll kind of look at this. So given a standard 6-sided die, what's the complement of rolling an even number? Okay, so this is called E. I know that's hard to see. Okay, so the event E, so even numbers, would be 2, 4, and 6. The event E complement would be 1, 3, and 5. Okay, so what's the sum of P even and P the complement of even, so odd? Okay, so first we have to actually figure out what either of those are. So PE is 3 out of 6, or 1/2. The probability of the complement of that is also 3 out of 6, also 1/2. So that got messy. So 1/2 plus 1/2 is equal to 1, right? 2/2, so we reduce that to 1. Okay, so that means that they are complements of each other. The probability of an event L is 0.9. What's the probability of L complement? So again, these two things, so the probability of L plus the probability of L complement has to equal 1. Right, so if the probability of L is 0.9, we can just use that to solve for our unknown here. So we're going to subtract 0.9 from both sides. 1 minus 0.9 gives us 0.1. Okay, so that would be the probability of the complement. Here we go. This was before my printer ran out of ink because it prints backwards. So the probability of mutually exclusive events. The probability of at least one of two mutually exclusive events is equal to the sum of each. Okay, so the probability of A or B, remember that this means or union symbol, is the probability of A plus the probability of B. Okay, so if we're spinning an evenly spaced 4-color spinner with red, blue, purple, and green, determine the probability of spinning a primary color or purple. So primary, remember, are red, yellow, and blue. Okay, so of these options, we have red and blue. These guys are primary. And then, or we want to look at purple. So if we look at, let's call this scenario primary color, let's call this event A. And then purple, we're going to call that event B. Okay, so PA is 2 out of 4, so 1/2. PB is 1 out of 4. Okay, so the probability using this formula of A union B, A or B, is the probability of A plus the probability of B. So in this case, we're going to have 1/2 plus 1/4. To add those fractions, we need a common denominator, so 2/4 plus 1/4. Oops. Quarter. That's going to be 3/4. Okay, and that makes sense because we can picture that spinner. If we've got red, blue, purple, green, the probability of spinning either one of this, this, or this is 3/4. We can see that. Okay. The probability of non-mutually exclusive events gets a little bit more complicated. Okay, so the probability of at least one of the two non-mutually exclusive events will occur is equal to the sum of the probability of each individual event, so PA plus PB again, minus the probability of the overlap. Okay, so in this case, if we think about the Venn diagram, we have this overlap. So if we take PA and PB, essentially what we're doing is double counting this overlap. So then we need to subtract the probability of those two things happening together that intersect. Okay, because up here, if we think about the Venn diagram for that last example, those are two separate events. There's no overlap here, whereas this one we have to subtract that overlap. So the probability of A or B is probability of A plus probability of B minus the probability of A and B. Okay, so this, as I said, prevents the overlap from being counted twice. If rolling an odd number on a 6-sided dice is event A and rolling a number greater than 2 is event B, then what are PA and PB? So the event A, okay, so rolling an odd number would be 1, 3, or 5. So A is equal to that. B is a number greater than 2, so 3, 4, 5, or 6. Okay, so the probability of A is, you've got 3 out of 6, which we could reduce to 1/2. The probability of B is 4 out of 6 possible options, so we could reduce that to 1/3. Okay, so when we look at the sum of PA plus PB, we get 1/2 plus 2/3. So again, we need a common denominator. It's going to be 3/6 plus 4/6. We get 7/6. Now remember how we talked about probability is always going to be a number between 0 and 1. This is not. This is an improper fraction. This is greater than 1. Okay, so this is greater than 1. Okay, so there's an example of why we need to subtract that overlap, right? This is like living proof that we can't have that overlap counting twice, otherwise our probability is greater than 1. Okay, so does this make sense? No. Why or why not? It's greater than 1. Okay, so determine the probability of A or B. We're gonna have to use that formula. So the probability of A union B, A or B, is the probability of A plus the probability of B minus the probability of A intersect B. So we need to actually calculate that. Okay, the intersect here is 3, right? 3 occurs in both and 5 occurs in both. So the probability of the intersect, so P, A, and B, is 2/6, right? So then we're going to plug all these things in. So I'm going to do them as this, right? We've got 7/6 for P, A, and B minus 2/6. Okay, so the probability in this case is 5/6. 5 of the 6 numbers would be one of those two events, right? The only number that's not included in either of these two sets is a 2. So that's that 1/6 that is not part of that probability. Okay, so that's why we have to subtract that overlap so we don't end up with a number greater than 1. A couple more examples. So if there's 4 red marbles, 5 green marbles, and 3 yellow marbles in a bag, if one marble is selected, what's the probability that it's red or green? So the first thing that we want to figure out is if it's mutually exclusive or non-mutually exclusive, right? Because that's going to tell us which formula we have to use. we're only pulling one marble out. It cannot be green and red at the same time, so that's going to be mutually exclusive, right? So that's the case where we have those two separate circles, okay? So then the solution would just be the probability of red or green, right? Red, union, green, red or green is just the probability of red plus the probability of green. So we can do those. 4 plus 5 plus 3 means that there's 12 total marbles. Probability of red is 4 over 12, plus the probability of green is 5 over 12. So we get 9 over 12, which we can reduce. Those can both be divided by 3. So then 3 over 4. Okay. Next example, a box contains 3 red playing cards numbered 1 to 3, and then the box also contains 5 black playing cards numbered 1 to 5. We randomly pick a playing card. What's the probability that it is black or has an odd number? Okay, so these guys are going to overlap, right? Because of those black cards, some of those are odd, so we're going to have an overlap here. Okay, so they are non-mutually exclusive. So we're going to have to use that more complex formula. So we're going to do the probability of odd and black. So it's the probability of odd plus the probability of black minus the probability of both of those things that intersect happening at once. Okay. So the probability of odd is, so again, there's a total of, there's 3 red cards and 5 black cards, so there's 8 total, right? So the probability of odd is we've got, so red, 1, 2, 3, and then black, 1, 2, 3, 4, 5. Probability of odd is 1, 2, 3, 4, 5 of those cards out of the 8 are odd. Probability of black is another 5 out of 8. Then we have to look at the probability of odd and black. So that's going to be 1, 3, and 5 here. So 3 eighths. Okay. So 5 plus 5 is 10 minus 3. We have 7 eighths as our probability. Okay. Okay. Another example, you roll a fair 6-sided die. What is the probability that the die shows an even number or a number greater than 3? Okay, so again, even would be 2, 4, or 6. Greater than 3 would be 3, 4, or sorry, 3 is not greater than 3. That would be 4, 5, or 6. Okay, so these are non-mutually exclusive, right? We have some overlap there. Okay, so the solution is going to be the probability, and I'm just going to use E for even, and then G for greater. So the probability of even or greater is going to be the probability of even plus the probability of greater minus the probability of both of those things happening at once, those intersects. Okay, that intersect is 4s or 6s. Okay, so the probability of even is 3 out of 6. The probability of greater is 3 out of 6. Minus that overlap, there's 2 out of 6 things contained in that overlap. So 3 plus 3 is 6, minus 2 is 4 out of 6. So we could reduce to 2 over 3. Okay, last page. So a draw box contains tickets numbered 1 to 30 inclusive. What's the probability that the winning ticket is a multiple of 3 or a multiple of 5? So multiples of 3 would be 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay. Multiples of 5 would be 5, 10, 15, 20, 25, 30. So what I can see here is that we do have a couple of overlap. So these guys would be non-mutually exclusive. Okay, so again, we're going to have the probability of, so I'm going to use T for 3s, and then, we'll use F for 5s. Okay, so the probability of a multiple of 3 or a multiple of 5 is the probability of a multiple of 3 plus the probability of a multiple of 5 minus the probability of both of those happening at once, so that intersect. Okay, so this is going to be 30 cards total, so that's going to be my denominator. Probability of a multiple of 3 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 30. And I'm not going to reduce because that's going to actually make my addition and subtraction easier because they're all out of 30. The probability of a 5 is 1, 2, 3, 4, 5, 6 out of 30. Minus the probability of those things overlapping. So either a 15 is an overlap or a 30 is an overlap. So there's 2 out of those 30 things that are an overlap. So 10 plus 6 is 16, minus 2 is 14, and then we can reduce to 7 out of 15. Okay, the last couple examples, this is how things are going to be on a test. It's not going to remind you like these other ones have been about mutually exclusive or non-mutually exclusive. You guys just need to be able to do that. So find the probability of choosing a penny or a dime from 3 pennies, 3 nickels, and 6 dimes. Okay, so you can't choose both of those at the same time if you're only choosing one, right? It's either a penny, a nickel, or a dime. So there's no overlap, so this is going to be mutually exclusive. So we're just going to do the probability of, we're looking for a penny or a dime, so penny or union dime is going to be equal to the probability of a penny plus the probability of a dime. Okay, so again, total, there's 4 plus 3 plus 6. So that's 13 total coins, right? So the probability of a penny is 4 out of 13. The probability of a dime is 6 out of 13. So you have a total probability of 10 out of 13. Last example here, find the probability of selecting a boy or a blonde-haired person from 12 girls, 5 of whom have blonde hair, and 15 boys, 6 of whom have blonde hair. So we want the probability of a boy or blonde. We'll call them hair, right? So boy and blonde hair, but we can't use B again. Okay, those things can overlap, right? There's of the 15 boys, 6 of those people have blonde hair, so that is an overlap. So it's going to have to be the probability of being a boy plus the probability of having blonde hair minus the spots where those overlap. So we've got 12 girls and 15 boys, so 27 total people. The probability of a boy is going to be 15 of 27. The probability of somebody who has blonde hair is the 5 girls who have blonde hair and the 6 guys who have blonde hair. So that would be 11 out of 27. Minus the probability that they are blonde and a boy. Okay, so that's the 6 of the guys who have blonde hair. So 6 out of those 27 fit both criteria. So 15 plus 11 is 26. Minus 6 is going to be 20 over 27. And I don't think that reduces, so there is our final answer. Okay. For practice, I want you guys to read page 98 to 104 and then do questions 1 to 16 on the following pages. So those practice problems. If you have any questions, let me know.